Welcome, everyone, and thank you for joining us for EMBCA's Hypersonic Challenges in the 21st Century panel discussion. My name is Luke Katsos, EMBCA's president, and I will be co-moderating today's panel with Technologist and EMBCA Director Eric Hill. Our distinguished panel for this discussion will include Hypersonic Propulsion PHD Researcher at the University of Central Florida, UCF, Adam Kotler, Aerospace Engineering PHD Candidate at the University of Central Florida, Robert Burke, and Congressional Candidate, Aviator, diplomat, former U.S. Naval officer, Commander Demetries Grimes. In August this past year, a Chinese rocket reportedly orbited the Earth before releasing a hypersonic weapon, which then re-entered the Earth's atmosphere and was guided to a simulated target, and which sent shock waves through the global military community. Hypersonic speeds are those in excess of Mach 5 or 3,217 nautical miles an hour, roughly 1 mile per second. Rockets have flown at hypersonic speeds in space since the 1950s, but the technology that allows hypersonic weapons to fly significant distances and maneuver around threats at high speeds is a relatively new phenomenon. These weapons can close in on targets, compressing the battle space in ways that may prove to be game changers in any new conflict. The US had led the world in hypersonic weapons development through 2014, when sequestration forced funding cuts to hypersonic research and development. Russia, China, North Korea, and Iran have hypersonic weapons programs, as do Australia, France, Germany, India, Israel, Japan, and South Korea. Funding in Congress for hypersonic weapons has been relatively restrained. However, both the Pentagon and Congress have shown a growing, more than growing, interest in pursuing the development and near-term deployment of hypersonic systems. This is due in part to the advances in these technologies in Russia and China that I mentioned a few seconds ago, both of which have a number of hypersonic weapon programs and have likely fielded operational hypersonic glide vehicles potentially armed with nuclear warheads. Recent US funding for HSW development has increased significantly across the services, and the outlook now is looking more positive. The hypersonic market and industry is poised to expand in a significant way, commercially and militarily, due to these and other developments with significant market impacts going forward now and in the coming decades. These developments and the geopolitical significance of the Eastern Mediterranean make this topic of discussion a timely one, especially for the East Mediterranean Business Culture Alliance, EMBCA. Although most geopolitical eyes are focused on the Ukraine and Taiwan at this time, the most dangerous part of the world geopolitically relating to Russia, China, and the West is potentially the East Mediterranean and what was known as in the past the powder keg of Europe, the Balkans. Hellas, Greece, is at its center, in particular as we head to 2023, the 100th anniversary of the Turkish Republic. We will explore in this panel discussion some of the background and challenges facing the US around the recent developments in hypersonics, the emergence of the modern global hypersonics race, the development history of hypersonics, as well as the technology and research that is taking place in this area, including both military and commercial applications, and also dual use applications. We will also as well discuss hypersonic infrastructure, hypersonic propulsion systems, and current hypersonic materials engineering. My co-moderator, Eric, will introduce today's panelists, Adam Kotler and Robert Burke, for some short presentations and I will introduce Demetries Grimes. After the presentations, we will have an open panel discussion with the panel and the moderators. But before that, I'd like to say a few words about our co-moderator, Eric Hill. Eric is a technologist in the third decade of his exceptional career. He holds a Bachelor's of Science degree in computer engineering from the University of New Hampshire. In the early 1990s, he was involved with the rapid expansion of network infrastructure and distributed management systems that culminated in the dot-com boom. Later, he explored and researched data warehousing and analytics to bolster the understanding of complex systems analysis. In the last decade, Eric has immersed himself in advanced automation efforts over critical infrastructure, as well as in various areas of cyber and cybersecurity, interfacing with a number of tech industry organizations such as Gartner and Forrester, and has extensive experience in the defense sector. His significant and acknowledged volunteer efforts have been youth-centered over those years, and with also a laser focus on STEM pipeline development, mentorship, and empowerment. In 2014, he has served, since 2014, he has served as the volunteer director of the Diaspora Hellenic Combatives program that has served the youth of Hellenic communities from Florida, across the US, into Canada. Since 2016, he has served as the advisor to the Sons of Pericles youth of the American Hellenic diaspora, and he has helped orchestrate and escorted numerous youth of the American Hellenic diaspora to visit Hellenic Naval Special Forces in Skaramangas in the Hellenic Republic. It was a first of its kind Nostros journey. In addition, he has had a long-term interest in the Hellenic Charter School concept as a vehicle for youth development in America. Welcome, Eric.
Well, certainly, thank you for that introduction. I didn't expect that. Before I introduce Adam Kotler, a brief comment. I was first introduced to Adam at a DoD office in town called the Central Florida Tech Grove. It's a very interesting fusion. So my basis with Adam was that introduction there, and kind of expanded out, and subsequently Robert. And with that being said, Adam Kotler is a PhD student at the University of Central Florida, conducting research on hypersonic propulsion concepts at the Propulsion and Energy Research Laboratory. Sciences, Inc., he worked as a development and test engineer for a novel engine combustor funded by a military SBIR, and we'll get into what a SBIR is a bit later. At Stellar Exploration, Inc., he worked as a development test engineer on the NASA Capstone and EchoStar satellite propulsion systems, performing ATP testing for flight hardware on the vehicle plumbing. The EchoStar vehicle has successfully reached space, flying on the Tyvak 0173, aka EG3, and has so far beat the CubeSat V5 world record by almost an entire order of magnitude. If all goes well between now and launch, Capstone will be delivered to space via Rocket Lab's Electron vehicle in spring 2022, where it will travel to the moon as the first spacecraft to test the unique elliptical lunar orbit. After Stellar, Adam joined Inversion Space, Inc., an LA startup developing re-entry vehicles, as one of their starting hardware development engineers. After acquiring invaluable experience at Inversion, he left to pursue his own vision at the UCF Propulsion Lab to pursue his PhD, advancing novel engine concepts for launch, space, and hypersonics applications. Adam is very passionate to advance the state-of-the-art hypersonics propulsion technology to augment our great nation's warfighter capabilities, and aims to lead younger generations, helping them to best leverage their diverse talents toward the everlasting vitality of the West. And with that, Adam, I'll pass it off to you.
Hey, everyone. Thank you very much, Eric, for that great introduction. And thank you, Lou, for inviting us to be on this podcast and inform the audience on the developing capabilities and technologies of hypersonics in the United States. As Eric had mentioned, I previously worked at some other firms. Beyond that, I got my undergraduate degree in mechanical engineering at Boston University. And without further ado, we're very happy to be here. So let's talk about some hypersonics. So I've prepared a little presentation that will go over just some high-level definitions of hypersonics to get everyone on the same page on some definitions and current capabilities in the West and for our adversaries. All right, so can everyone see my screen?
Yeah.
We seeing a black screen, or we seeing the presentation? Ooh.
We see a black screen and we see next, and there we go. Okay.
There we go. Finally got it set up. Great. Awesome. Okay. So hypersonic speeds, Mach 5, otherwise known as 1,130 feet per second or a mile a second, just over a mile a second. So the reason hypersonic speed is determined at this particular Mach number is because of the effects seen at Mach 5 and beyond, right? There are unique flight conditions that a vehicle will see at Mach 5. It'll see some of these effects in Mach 4, but they begin to dominate at Mach 5 and higher Mach numbers, right? So what are some of these effects? Well, you have extreme shock formation around the vehicle past Mach 1. And then as you get to Mach 5, these effects become more extreme and you start to get extreme heating. You're flying through air, right? Your vehicle's flying at very high speeds through air, and it becomes akin to like sort of flying through sand, right? So you can sort of imagine the extreme drag that a vehicle would experience as you're flying at these speeds, right? When you fly at these speeds, right, you get that aerothermal heating around your vehicle, leading to a lot of heating problems for your vehicle, and this can incur severe engine thrust limitations, on top of which you'll have to consider a lot in terms of the engineering design. Right. So, what are some of the tactical implications of Mach 5 offensive capabilities? Right. So, it's primarily in speed. You're moving at very fast speeds, and on top of that, these vehicles can be highly maneuverable, which make them very hard to detect and track. Right. So, the idea here is that these weapons can surprise. They're supposed to surprise your enemy's defense capabilities, creating so much chaos in their system that they're not able to respond effectively in time to a threat, right? On top of that, there's also implications for high-speed cargo delivery and personnel delivery as well, right? So transporting your units faster from one place to another, right? So I'm going to talk a little bit about the history, right? So the ability to travel at Mach 5 could not, and at hypersonic speeds, could not be accomplished without revolutionary advancements in the propulsion technology that's used to propel these vehicles to these speeds, right? So there are different types of engines to be used, right? In your conventional subsonic systems, you have turbojet and turbofan type propulsion systems. Those are good to maybe, you can push up to, you can push like a little bit beyond Mach 1, Mach 2, but beyond that, they're incapable of bringing your vehicle to higher speeds. That's where the ramjet, rocket engines, and scramjets come in. These concepts are well over a century old, but they were sort of ahead of their time when they were invented. And, there was a lot of groundwork to be laid back then to field them as actual propulsion systems on their vehicles. So a ramjet could essentially work and get you between Mach 3 and Mach 6. The idea behind a ramjet being, as your vehicle flies towards air, this incoming air can be used and decelerated to higher pressures within your engine to achieve that combustion that you need to accelerate you beyond supersonic and hypersonic flight. Right, this is good between Mach 3 and Mach 6. Beyond that, you'll start to want to transition to a rocket engine or to a scramjet. Scramjet being a supersonic combustion, right? So instead of decelerating your gases in your air completely to a subsonic speed within your engine, you're still keeping it supersonic and you're combusting it in a supersonic state, right? So a lot of you may remember the X-15 program, the famous X-15 program back in the 20th century, during which Pete Knight reached Mach 6, fastest manned travel in history during the X-15 flight on October 3rd, 1967. Little known fact, Neil Armstrong was actually an X-15 pilot before he became an Apollo astronaut. On top of that, it's very easy to overlook that a lot of the spacecraft that we've already developed, such as the space shuttle, they easily exceed speeds upwards of Mach 20, Mach 25 during reentry into the Earth's atmosphere, right? So a lot of these vehicles can claim, right, hypersonic capabilities, hypersonic reentry capabilities, right? So I'm going to do a little time skip here and take us to the types of vehicles we have today, which are hypersonic glide vehicles and hypersonic cruise missiles. These are the two primary types of hypersonic vehicles and weapons being pursued by the United States and its adversaries today. Right, so starting with a hypersonic glide vehicle, these vehicles are typically launched from like a conventional means, like a rocket, and then they're deployed from atmosphere or beyond atmosphere, after which they rely upon momentum and control surfaces to be directed and reach their target. These vehicles can reach speeds in excess of Mach 5 and plus, and their warheads can be either conventional or nuclear. Difference here being that conventional is more like a kinetic energy, a kinetic type payload with metal shrapnel and a smaller explosion, whereas a nuclear warhead is exactly as it sounds. You deploy a nuclear payload that detonates and has some blast radius of effect. Right, these vehicles, they sort of look like the B-2 stealth bomber, in that they're sleek aircraft. And as far as the nations developing these capabilities, right, there's USA, Russia, China, North Korea. These are the folks who have at least tested the hypersonic glide vehicle. Japan and Germany are also looking to develop their own capabilities in their own hypersonic glide vehicle programs as well. Right. So then the next type of vehicle is a hypersonic cruise missile. These are more akin to your conventional cruise missiles in that they fly at lower altitudes. They're launched by some conventional means before a scramjet takes over, accelerating them to Mach 5 plus speeds. Warheads can also be conventional or nuclear. So pressing forward, this sort of leads us to some of the headlines that have been, on everyone's minds these past couple of years, and this is with regards to developments abroad by our adversaries in Russia, China, and North Korea. Right, they all have their own hypersonics development capabilities, which include hypersonic glide vehicles and for cruise missiles. And their focus is on developing these vehicles and these weapon systems for nuclear payloads. This is a very important distinction. We'll get into it later, right? So Russia has the Avangard hypersonic glide vehicle and the Kinzhal ballistic missile, as well as the Zircon HCM. Russia has actually been able to field the Kinzhal ballistic missile. And on top of that, they've got some unknown number of hypersonic wind tunnels available as ground support equipment through which they can test some of their designs and some of their systems. China, similar development. They've got their own hypersonic glide vehicles with the DF-ZF vehicle and the Lingyun hypersonic cruise missile. On top of that, they've got the Starry Sky 2, which is sort of similar to, it's a vehicle that's a little bit more similar to the X-15 type vehicle. As far as tests go, they've performed at least 20 times as many tests as the United States. They've got 21 hypersonic wind tunnels, and they're looking to advance their capabilities to test up to Mach 30 by this year. North Korea, this one's a little bit new. Not much is known about their development, but they've at least performed 3 tests of a hypersonic glide vehicle since September. Some of the other folks developing these programs include our allies, right? Japan, Germany, Australia, and India. They've all got their own programs and goals to develop cruise missiles or glide vehicles and some number of infrastructure and ground support equipment to test the unique hypersonic capabilities on the ground as opposed to in flight. Right, so this leads to the question, okay, we know what the development abroad looks like. What does it look like in the United States, and are we lagging behind? So the answer is not a yes or no. It's not a short yes or no. It's more nuanced than that. In some ways, we're ahead. In some ways, we're not, right? So the primary difference I want to highlight here between the United States hypersonic vehicle and weapons programs between our adversaries is that our capabilities are directed more towards development of conventionally armed warheads and payloads as opposed to nuclear, right? Now, what implications does that have on the technical developments? Well, since you're conventionally armed, your targets are going to be smaller scale, and what that means is that they're going to require higher accuracy. Because they require higher accuracy, it's a much longer development roadmap than something like a nuclear warhead that can be essentially delivered with maybe 10% missing accuracy and still be able to reach its target due to the effective blast radius of the nuclear warhead, right? So the United States has, at the moment, at least 10 programs going on that's published. These programs are published, and the different branches of the DoD, they all solicit and they all propose their budget requests at the end of the fiscal year to acquire their funding for their own programs. So DARPA's got a few programs, as well as the Army, Air Force, and the Navy, right? So what do our defenses and infrastructure capabilities look like? Well, the Missile Defense Agency has this hypersonic defense program, which is used to assess defense options, including interceptor missiles, hypervelocity projectiles, laser guns, and electronic attack systems, as well as space-based sensors to advance hypersonic detection and tracking technologies. We've got 48 confirmed hypersonic facilities that can emulate unique hypersonic flight effects. And the DoD is currently evaluating capacities of current facilities and requiring investments to support testing. These particular efforts have ramped up, particularly in the past couple of years, in light of developments made abroad. There's another side to hypersonics flight, aside from defense, and it's easy to overlook this, and that's in commercial hypersonics, right? So think about the success that SpaceX, Rocket Lab, and Blue Origin have had in decreasing launch costs for space payload experiments by at least an order of magnitude compared to what it used to be in the late 20th century, right? This type of success is extending to aerospace in general, and in particular commercial air travel, right? Where we've got a ton of folks who want to build supersonic and hypersonic commercial airliners and vehicles to essentially transport just civilians and passengers and their cargo to places around the world at never before seen speeds, right? So on the commercial side, there are a lot of different technical and non-technical challenges to address that defense may not necessarily be directly targeting as well. Now, commercial development of hypersonics is really good primarily for two reasons. The first being these commercial hypersonics companies, they set their timelines at a more longer term vision than some of the defense programs that the United States organizes their budgets for, right? So Bryce Tech and Deloitte, some names have done like these reports and market research on the development timelines of a lot of these companies. And what a lot of them are seeing is that their prototypes, their flight demonstrations, and their minimum viable products all seem to converge around this date, 2040. So the vision is hypersonic commercial travel by 2040, right? Which is great news. It means that the commercial side is developing these long-term plans to ensure the success of developing hypersonic capabilities, right? The second reason this is great is that as these prototypes and vehicles start advancing and becoming more fieldable, they'll be able to be used as platforms in which the government can test other hypersonic technologies like sensors, maybe some novel engine concepts, and other types of technologies that can also accelerate the development of hypersonics on the defense side, right? So hypersonic transportation, if that can be achieved, it will bear revolutionary lifestyle implications to humanity, right? A lot of folks in, I used to live up in Boston. I met some folks who would actually wake up in Boston and they'd go to their day job in New York, right? They'd take the train, actually go to New York and work there for their day job and come back, right? That's how they live their lives, right? So imagine, you know, in the case of Hypersonics 2040, imagine waking up in New York and then going to your day job in LA, vice versa, right? It's a long ways away, but that's sort of the big idea with what we could do here, right? Now let's take that a step further. Imagine waking up in LA and going to your day job in Singapore, right? It has the potential to connect us more than ever before seen, right? So a lot of the value propositions that you'll start to hear is New York to LA in an hour or less, right? So some of the supersonic folks who are looking to achieve supersonic flight as a pathfinder to hypersonic flight are Ariane, Spike Aerospace, Lockheed, and Boom. On the hypersonic side, you've got Boeing, Hermes, JAXA, Stratolaunch, and Generation Orbit. These are some of the names that I pulled out from the Bryce Tech report, and there are a lot more players here. Hermes is of particular interest. They're out in Georgia, and they recently came out with a quarter horse vehicle mock-up. I think it was a mock-up or a prototype. And then at the back of it, they fired their one of their combined cycle engines that they want to use to propel this vehicle, right? Okay, so I've talked a little bit about defense and commercial. Now I want to talk a little bit about what we do at the University of Central Florida Propulsion Energy Research Lab, or PEARL as we call it, right? So at this lab, myself and Rob, we're focusing on the design, testing, and evaluation of state-of-the-art hypersonic propulsion concepts. This extends to ramjets, rotating detonation rocket engines, and shock-based combustion ramjets. We've also recently received a DoD grant in the amount of $1.5 million to develop technologies, solid rocket propulsion technologies that would compete with some of the propulsion concepts coming out from Russia and China, right? So how is a university lab like ourselves funded and supported, right? Well, we primarily work for folks in the DoD, such as the Air Force Research Lab, the Naval Research Lab, Office of Scientific Research, and even acquire some grants from the National Science Foundation, as well as Department of Energy. We also rely upon generous donations made to the Cater institution here at UCF, which is the Center of Advanced Turbomachinery and Energy Research, under which the Propulsion Energy Research Lab works. We've also made some great connections by leveraging the Center for Entrepreneurial Leadership. It's Eric sort of talked about how we met. That's the Center for Entrepreneurial Leadership there definitely helped out, and we're very much grateful for that. So in summary, the United States, Russia, China, and North Korea have all demonstrated successful hypersonic weapons capabilities, but the US has not yet fielded any hypersonic weapons, right? The United States goals for hypersonic capabilities, though, tackle more difficult technical challenges, which may be the reason for extended roadmap and extended development, right? Commercial and defense industries are likely to work closely to advance each other's goals. And on top of that, we're working at the forefront of novel hypersonic propulsion solutions to develop advanced propulsion solutions for future capabilities. Right, so I'm going to pass it over to Rob, and Rob's going to speak on some of the technicalities of hypersonic propulsion.
Before you do that, let Eric introduce Robert. Just a small question, Adam. How many other universities have these type of programs? Right.
Yeah. So there are. We're definitely not the only university performing this type of research. It's going to require an extended effort across all labs in the country. We are one of the UCF is one of 3 propulsion labs working on really advanced state-of-the-art forefront propulsion technologies. However, there are a lot of different other universities working on other aspects of hypersonics, including like aerodynamic effects on the body, thermal management systems. So yeah.
Okay, Eric.
No, perfect segue into Rob. And before I do my introduction, anybody in the audience note that's not a photo in his background. He literally is in a lab right now. So I'll be talking a little bit about Robert. Robert Burke is a PhD candidate at the University of Central Florida in Orlando, Florida, in the United States of America, for those that of our folks that are in foreign countries. He studies aerospace engineering with a focus on propulsion systems. Robert is a research scientist and physicist at his core. He's one of a small group of researchers around the world that studies detonation combustion, a rapid and powerful new mechanism for burning fuels in an engine. He has much experience with the U.S. Department of Defense in his work with the Air Force, the U.S. Navy, and the Pentagon in several various propulsion contracts. Robert emphasizes his mentorship in the sciences more so than his technical knowledge, working on a U.S. National Science Foundation student research program and leading peer mentorship seminars for university programs. Robert is originally from Hawaii and still loves being out on the water and cooking good food. We need to meet in the Eastern Med at some point, I think.
Absolutely. Thank you very much for your introduction, Eric. And also, I'd like to thank Lou and the others here that are in the panel for the wonderful conversations we'll be having today. So I'll be talking a little bit about more of the technology side. I did also provide a few pictures and such because I realize it's probably really difficult to talk about propulsion systems without some visual aid here. So let me also pull those up as well and make sure we have that visible. So as I mentioned, I come from, and as Eric had introduced me, I come from more of an engine design background and a lot more of the technology side. So as far as the implications of the technology, I'm going to leave it up to some of the finer gentlemen here on the panel to talk more about that. But I do believe that in general, when discussing especially a very high impact technology like hypersonics, it's pretty important to understand how the technology actually works. So I'll be starting off first with, in general, how engines operate. At its core, any propulsion system relies on pressure and it relies on temperature in order to create some kind of power that's used for thrust. So in the case that I have shown here, let's say the turbojet engine, this is what you would have in anything from your airplanes, your commercial airliners, all the way up to some of your fighter jets and such. Pretty much all of that technology does is it takes the air that you have going through the air, it increases the pressure, and then you burn a little fuel in it and to increase the temperature, and then you have thrust. That is pretty much how every engine works, and that's pretty much how every engine will work in the future. So in some of the engine technologies that Adam had mentioned previously, there's also the ramjet and the scramjet engines. Those also work under the same operations. If you look at the little plot on the right here, it actually shows that as you're going axially through the engine itself, you can see on this top plot being the pressure. You see there's an increase in pressure through the engine, and that drops off. You see there's also an increase in temperature as you burn your fuel and the air that you have going through it, and that also drops off. But in the end, you have an increase in your velocity, and that's pretty much your thrust that's being produced. So pretty much pressure and temperature. That's pretty much an aerospace engineering degree. You could pretty much get the document tomorrow. Now, as far as a bit more specifics of the actual engine themselves, so I have here a mock-up of or a cutaway of a ramjet engine, and I have here boxed in. Let me actually pull out the laser pointer that I have here. I have boxed here kind of the different major components of the engine and what they actually do for it. So this first initial portion that I have boxed here in blue, this is known as your compressor. All this does is it takes the air that you have flowing through your engine, which again, I'm going to be talking primarily about air breathing engines. So they go through the air, they don't go into space per se. All it does is it takes your air and increases the pressure to it. And again, this goes back to the whole performance of an engine. This part that I have here circled in red, boxed out in red here, is where you introduce your fuel, and then you light off the fuel with the air. And that's where you have your increase in temperature. And then again, at the very end, I have here boxed in yellow. This is where you take all of that pressure and all of that temperature that you have built up, and it, puts it into a utilizable form of energy, being your thrust. And that's pretty much how you have any engine move forward. So I gave a background on that because I'm also going to be showing some schematics of some other engines and such, and it'll be very easy to be confused by some of the different shapes and everything on here and just all the different designs. But just I want to say that again, all engines really operate on the same way. But now I have shown here a scramjet engine, which, as Adam had mentioned, these are the engine types that are primarily going to be used for when you're getting up into your hypersonic regimes, being anything above Mach 5, where Mach number, just to specify, is the speed of sound. So a Mach number of 5 would be 5 times the speed of sound. As a baseline, for example, like a bullet coming out of a gun would not be going Mach 5. It'd be actually going a little bit faster, a little bit slower than that. So actually, we have some vehicles that are entering the atmosphere and that we have some capabilities that, are very dangerous, So we'll be talking about that as well. But with regards to how a scramjet works, you have this inlet portion, which is meant to capture your air. And there is this top portion is known as your shock cone, and this bottom portion is known as a shroud or cowl. And these red lines that you see that are showing here, these are shock waves. So anytime that you're moving very, very fast through the air itself doesn't have enough time in order to actually move out of the way. So you're compressing the air until it forms a shock wave in a sense. And for those of you, who have seen, like, let's say a rocket launch, or those of you who have seen like a fighter jet or something flying over an air show, you'll hear those loud booms. That's actually the sound of these shock waves. The compression of all this air, it's a very, very energetic and very, potentially violent phenomenon. But how this engine works is that it creates a shock wave, which you have propagate throughout your engine. And what's important to know about a shock wave is that as a shock wave propagates through air, it increases the pressure of the air around it. So you can probably understand maybe where the use of the shock wave is coming from based on the pressure and temperature discussion that I just talked about. Essentially, though, you capture these shock waves, which move about through your engine. You introduce your fuel into it, and the actual pressure and temperature of the air that's coming through there is enough to actually oftentimes auto-ignite your fuel and then create a high rise in temperature. And thus you have a flame that is coming out the back end, and you have, the rest of the design of your engine is in order to contain all of the energy that is being produced from this and directing it in a way in order to move forward. So again, I don't want to say that a scramjet is very simple, but it is pretty simple to follow. So some of the things I'd like to mention, though, are some of the regimes. Again, Adam had mentioned that your scramjet engines are going to be used for above 5 times the speed of sound, Mach 5. I think theoretically they're capable of going up into the Mach 12 to Mach 20 regime, so they can go incredibly fast. But as Adam had also mentioned, there are kind of some barriers. This technology is deceptively simple, but for example, there's a lot of very important technical advancements that need to be made. One of them that I'm going to talk about is temperature. So as you're going through the air this quickly, Adam had made a nice metaphor of a vehicle going through sand. And it is because as the vehicle is traveling through the air itself, as it touches, all parts of the vehicle, the inside, the outside, and everything, it drags up against it, and it creates friction and it creates heat. And going at, Mach 5 speeds, your surface temperature of these vehicles could be going up to the 2,000 to 3,000 degrees Fahrenheit. For those of you who don't know, that's enough to melt steel. So you kind of start having a limit on, some of the materials that you might need in order to actually build these vehicles. So that's just the surface of the vehicle. For example, this tip here at the front, that can get upwards to 4,000, 5,000 degrees Fahrenheit. And it's because it's a very small tip and there's not much surface. And the thing is that geometry is very important in the development of these shock waves. So we can't get around that. So this kind of is leading into some of the challenges that I'll also be talking about as well on the design of these vehicles, but also some other things too. These hypersonic vehicles could be ranging anywhere as far as flight altitude between 50 to 90,000 feet up in the air, which is quite a bit higher than your conventional 30,000 to 35,000 feet that your commercial airliners are at. Slide. Okay, so to show you that, it's more than just technology. It's more than just designs right now. Here I have an image actually of the Army's X-51 hypersonic missile. And I just kind of want to show you again the similarities that, this technology, we know about this technology, and it is out there and we are designing it. But again, there are still quite a few barriers that we have in order to actually fully have it as the technology that we're going to be talking about today. As I mentioned a little bit about materials and such, we can talk about this also during the panel session as well, but especially for hypersonic vehicles, I would strongly say that material science is very much lacking in the development of these vehicles. You wouldn't want to be flying a vehicle that would disintegrate after flying for 10 seconds when you need it to fly for 30 seconds or a minute. We simply can't have that. So I can talk a little bit more about that during the panel discussion as well. But I also want to talk a little bit about some of the differences of the different hypersonics vehicles that Adam had mentioned. So there's the hypersonic glide vehicles and the hypersonic cruise missiles, or the hypersonic ballistic missiles. So the reason why there's kind of a distinction between the two is in two part, one being their function and the other one being kind of the flight conditions and the flight path that they would go through. So let's talk more about the flight conditions and path first. So our traditional missile styles, our ballistic missiles, are called as such because they follow a ballistic path. We would send them up into the air, and then they would come down onto its target. The thing is, ballistics have been something that have been studied since, the BC times, pretty much ever since physics has been, established. And it's very straightforward to be able to calculate where these missiles will be going, because again, it's a concrete science. This is where I'm going to talk about the boost glide vehicles, in that they can be very surprising. So how these boost glide vehicles work, these hypersonic vehicles, is that they come through an initial boost stage where they initially shoot up right at, pretty much straight up like you would have a rocket, that like SpaceX or, NASA would be launching. After that, it would go into a short ballistic trajectory where it would start to head back towards the Earth in a, parabolic kind of shape. At that point, the propulsion system that was on the boost glide vehicle, which is typically just a rocket, that at that point it would detach. The boost glide vehicle would go into a short U-bend and then approach its kind of coasting or gliding stage. Pretty much all of this initial part is in order to get the boost glide vehicle the kind of the run-up distance, the speed, in order to get up to Mach 5 or above. So during this portion where it's coasting flat, it is traveling at a very, very fast speed. Is at the Mach 5 speed or above. And that's where it also takes the most of its distance. I think what either has been said or will be said later on today is that with a lot of these hypersonic vehicles, a lot of these hypersonic capabilities, is that these can be launched from pretty much anywhere in the world and be able to, target anything anywhere around the world within, about an hour, or just a little bit over an hour. So very far-reaching implications, and a lot of that comes again from this cruising portion here. At this point, though, at any point, that boost glide vehicle, when it's about to reach its target, could then dip down in its reentry and pretty much, immediately hit its target. Which is what makes especially the boost glide vehicles very, very frightening, in that you can't really tell where they're going to be going until they're pretty much about to hit its target, which is oftentimes too late. But then moving on to the other vehicle type, being the hypersonics cruise missiles, these are a bit more like your typical missiles, except for the fact that they're going at very, very high speeds. So I would like to kind of akin them to just more a straight trajectory. That's why they're also a bit lower to the ground. It's simply the applications of these is that you would launch them and pretty much they would get to your target before the target really can see it coming. So it's primarily on the speed basis here. But again, some reasons why I wanted to kind of explain some of the differences as well between the different vehicles is also kind of talking about, what their functionality would be. And also a little bit about some other barriers and such for hypersonics, and just kind of informing everyone about that. But for example, talking about a hypersonic glide vehicle, Again, you would launch it up into the air. It would cruise about Mach 5 to Mach 12 at speeds, and then it would dip down when it has its payload. As Adam had mentioned, there's different types of functions to these vehicles, and such as their payloads. Adam had mentioned nuclear, being pretty self-explanatory. He'd also mentioned the ballistics as well, where these glide vehicles, given their shape and such, when they're on their reentry, they can actually oftentimes they dispose of either some wings or such, or they launch a certain type of projectile or something. Again, for the nuclear cases, it's pretty self-explanatory. But Adam had mentioned with the ballistics, just this vehicle itself, there would not need to be any kind of explosives or anything on there. If a vehicle like that were to just impact the Earth at the speed it's going, would be enough to destroy a city. That's how fast and how powerful these vehicles are, and how much these can be seen as weapons. But as a part of this, I also want to show this graphic had a good diagram here with regards to communicating, and also ultimately being able to find out where these vehicles are, especially when they're up in the air. And that goes into countermeasures and such, and how to figure out where these are. You can pretty much look at these vehicles from either up in the air, I guess not up in the air, up in space, being your satellites, your low Earth orbit satellites, or down on the ground. All of this is primarily done with your via your radio waves and such, very much like how we communicate with anything that's up in the air right now. The reason why, for example, satellites are now even more important for being able to monitor where these vehicles are is given the fact that some of these vehicles can be traveling at, again, now incredibly high altitudes, starting to approach that range where satellites, it's kind of almost in that domain with your low Earth orbit satellites and such. Now, however, though, of course, there is an issue that these vehicles are moving very, very quick. Another part of that, besides being able to keep track of these vehicles, and also being able to either have some kind of warning system or something, given that these vehicles are traveling so fast, and at the point before it hits its target has minimized by a factor of 10 to 100 times compared to your conventional, is also in part because of some of the physics that's also involved with what happens when you have these vehicles moving at such high speeds. So one of the things I'd like to mention, and it's one of numerous other things that I can talk about during the panel, but one of them is actually when you have these vehicles traveling so quickly, the heat that I was talking about that generates on the surface of these vehicles and around these vehicles is so much that it would actually take the air that is there, and it would actually, in a sense, melt it. It would change its state. If you've ever heard of plasma, it's kind of that fourth state of matter. If you've ever it's a fun science experiment that I've heard of. I've tried not to do it because I've heard that you can destroy your microwave because of it. But if you've ever tried to microwave a grape, you'll notice that it kind of arcs with electricity and such. And it's actually because of that heating that's causing it's causing ionization. It's causing the matter that's in the grape in order to change to a different state. And that ionization that you would see on that grape is actually what's happening on the surface of these vehicles. Because of that, very much like how the microwaves are creating, lightning on a grape inside your microwave, very much on that side, when you have this going around your vehicle, when you're actually trying to pick up where this vehicle is by beaming radio waves at it and seeing if you have anything back, the vehicle itself will actually absorb a lot of that radiation. And you actually can't tell that anything is there because a lot of your radio signatures are not being reflected back off the vehicle. So it's actually something that's almost inherent to going at these speeds, is that it's very difficult to actually tell if these things are there, because in our modern conventional methods of being able to tell where something's at, pretty much it's invisible to those radars in a sense. So that's something that I want to bring up besides some other things and such. But kind of going on to that as well, I also wanted to kind of, again, a big part of this is also talking about hypersonics and where it's going right now, and how should we be navigating this kind of terrain. I just want to give an example of right now one of our current warning systems. Again, I can primarily speak on the United States, being from here, but we have our North Warning System, where it's a collection of radar systems that they're meant to be able to track anything that is coming into our airspace and being able to very rapidly and very tell what it is, where it's coming from, and whether or not it's considered a threat. And again, I want to showcase this here that, we have a pretty good wall per se of being able to tell, what things are coming in and, if there are any threats that are coming in. But as I just mentioned in the previous slide as well, some of these systems that we have right now, they are going to need to be adapted. They're going to need to be molded for this new type of technology. So again, I don't mean for it to come across in a very negative or very frightening way, but it's the reason why we're having these conversations today, so that we can talk about this kind of stuff. So again, my hope is that if there's any technological questions or anything as far as like the design process, I hope that I can answer any questions during the panel session on that. But that concludes what I can talk about for right now.
That's great, Robert, and thank you, Eric. We'll discuss in the open panel discussion the material engineering that's required for some of these systems. But a lot of the things that you discussed, Robert, have to do with ground-based systems and the use of satellites for monitoring those missiles or what have you. Are there any thought processes in terms of having these weapons in space itself? In other words, acting as sort of not satellites, but satellites to launch these things, or is that problematic?
It is a bit problematic, given that with a lot of these vehicles, they're meant to be, a big part of these vehicles is the fact that they can run off of air. So at a certain point, you can get too high up where you can no longer utilize the air that's in the atmosphere. But also another part of this too is that, technically, if you were to look at how high some of these vehicles are going, they are getting very much up there. So I don't think we'll necessarily ever be seeing missiles or such, flying through space and kind of hanging around there and then coming down, given the fact that at that point, we would kind of consider them more as, your typical rockets and your ICBM missiles and such. But okay. Yes, they do get high up there, and we will be seeing them up there. That's kind of the reason why they go up really high. So.
Thank you so much, Robert. I'd like now to introduce Commander Demetries Grimes. Commander Demetries Grimes, U.S. Navy retired, is a lifelong Central Floridian. He's a second-generation Navy veteran. He's the son of a Greek immigrant mother. He's combat decorated and a former U.S. Navy officer. He's an aviator. He's an Afghanistan war veteran. He's been a diplomat in Greece and Israel. He's been an executive and a published writer on national security and foreign affairs. He has completed 7 deployments, more than 100 combat missions flown from aircraft carriers, including 2 deployments to Afghanistan. He has served as a military prosecutor and head judge in enemy combatant detainee trials of Al-Qaeda, Taliban, the network, the Hypersonic network, and other captured terrorists. He is a Secretary of Defense Executive Fellow, a former White House military aide, and has served in strategy and leadership roles at the Pentagon and NATO headquarters. Demetries has an MBA from the London Business School and a BA in International Relations from Boston University. He has completed postgraduate studies in strategy and national security decision-making at the U.S. Naval War College and crisis response operations at the NATO School. His awards include, among many others, 3 Defense Meritorious Service Medals, 5 Strike Flight Air Medals, 5 Navy Commendation Medals, including Combat V for Valor, Israeli Defense Forces Medal, 2 State Department Meritorious Honor Awards, and various campaign awards. Demetries is running for the new congressional seat to be established in Central Florida. Welcome, Demetries.
Hey, thank you, Lou, for that kind introduction, and Eric for having me along with your distinguished panel. And I'm running as a Republican for the new seat. This topic is near and dear to me and my concerns, as indicated by my my life of serving the nation. And we touched on this earlier before we started. In my tour as a Secretary of Defense Executive Fellow, this is one of the topics that we had discussed quite often with regards to the fact that our procurement systems are not geared to stay to keep up with the advances that we're seeing in weapons technologies. And what we're dealing with right now is a whole new evolution or revolution in warfighting concepts with these weapons that I guess the modern day equivalent would be, the transition from wooden ships to ironclads, or from ships of sail to steam engines and such. So one of the unfortunate things with the way that our budgeting system is that that's actually playing to the advantage of our adversaries, because they can actually dedicate the full force of their government and the resources of their government into getting them up to this, what we saw with the Chinese, which is basically this will go down in history. Their hypersonic missile test is the modern day Sputnik event that we're dealing with, right? One of the things that we had discussed in the fellowship, the Secretary of Defense selects 2 officers from each service every year to go out and be mentored by Fortune 500 leadership teams to bring back new ideas on how we can use technologies and make shifts to organizational structures to be more efficient and effective at what we're doing in the DoD. And I'm a big history buff too, and I appreciate what you discussed earlier about the SR-71 program, and that's an example of what we need to institutionalize within the DoD to stay ahead. Because back when the SR-71, without getting into too much detail, but the typical process from when we identify a requirement for a particular weapon system to the time that we actually get the first prototype going, that it's already outdated. It could take 10 to 15 to 20 years, which we're seeing with F-22, F-35, right? And what was revolutionary about the SR-71 is that they were able to bypass, the traditional oversight and secure the funds required to do what they needed. And so from the time they identify the requirement for the SR-71 to the time that they actually got the first prototype flying, I think it was somewhere between 13 and 15 months. So that's something that we need to, and I'm sure, I no longer have access, but I'm sure there are some great minds that are thinking of how we can do that. But those are just a few. I have so much that I can say, but I want to hog up the panel's time so we can get into the discussion. I'm happy to throw in on more details.
Thank you, Demetri. And as a matter of fact, when we can start the open discussion right now. I do want in the next few minutes, not right this second, to discuss also what's happening in the East Mediterranean, and some of the things that we talked about obviously impact directly on the Eastern Mediterranean. Would everybody like to just go off mute, because we're going to have an open discussion right now? And one thing that was a little bit of a shock to me, Adam, I have to be honest with you, is when you talked about commercial applications, in 2040, which I found kind of shocking, to be honest with you. I remember, and I think we had this conversation when I was much younger, and it was Mach 2. I was flying in a Concorde, to go to Paris, and I'm saying to myself, here we are in 2022. I don't know, 30 years ago, I was flying into Paris in like about 3 hours, and we're like in like barbarians. I don't get it. Can you explain, like, why is everything happening so slow, Adam, if you can?
Sure. So there's two sides to this. There's why it's slow commercially, then there's why it's slow on the defense side. We can talk about the commercial first. So, right, yeah, you mentioned, I think it was the Concorde, right, Lou?
Yeah, the Concorde.
Right, yeah. So there was, I can't remember the exact date, but there was one particularly nasty crash with the Concorde that sort of tanked the entire program and tanked the sort of the demand.
I got it. But
right.
I flew 30 years ago. I'm talking about 30 years ago. I flew in a Concorde. 3 hours. I was in Paris. I was, drinking a drink, and then I was in Paris meeting with IMP for some architectural building.
Right.
I just find it shocking with all this technology that we've had since the 1950s or what have you. And all of a sudden, other people are bypassing us, and we're like in the Stone Age. I don't get it, Adam. I really don't.
Right. Yeah. So commercially, there's a lot of technical and non-technical barriers that are a little bit different than the barriers that the defense side is going to have to face. In particular, the type of the sort of per se target audience and target market. There's a different market that the commercial side wants to cater to, and they sort of have to deal with perceptions of the public to these programs, right? And you can see this in the Bryce Tech and the Deloitte reports. They're trying to analyze all the ways the market can be de-risked to maximize profit and the success of these different programs. What they're finding by interviewing a ton of these aerospace companies is that there's a lot of negative public perception towards the emissions of these vehicles. And as well as that, there's a lot of infrastructure capabilities, like ubiquitous infrastructure inadequacies that will need to be developed in order to be able to accommodate the supersonic and hypersonic vehicles. So, included in there is sort of like, do we have the runway infrastructure required to slow down these vehicles that are going really fast? Do a lot of combustion and fueling resources and research is going towards hydrogen combustion because it's cleaner combustion, right? So now, if you're using hydrogen combustion, are you going to use a liquid or a gas? If you're going to use liquid hydrogen, it's going to be cryogenic, which means it's going to be much more expensive and require radically and revolutionarily new ways to store this, to store the fueling on site, at these airports, so that you can actually service the vehicles and fuel them. Those are some of the non-technical barriers highlighted in the Bryce Tech reports. And on top of that, they want to know, is there like an actual market? Is there like an actual viable market for hypersonic and supersonic flight? They've noticed that there is a very high demand for supersonic flight. But then as you start going to hypersonic speeds, the value proposition starts to decrease because you have a lot of that time is in taxiing, right? Taxiing starts to take up a lot of time, and then you're not gaining as much speed when you start going Mach 6, Mach 7, as opposed to just Mach 5 or Mach 4.
Well, I got to tell you, I was thinking when you were talking about jumping on a plane from New York and going to California, what have you, in an hour, or Singapore or wherever, I was thinking that I'd be at the airport for 2 or 3 hours before I got on the plane.
Exactly.
Robert, can I ask you a question? Can we go a little bit into more depth in terms of the material engineering required for some of these things we were talking about, especially with the temperatures that you were dealing with?
Yes, absolutely. And actually, really quick, just to kind of piggyback off of a little bit what Adam had said, a lot of it also is regulation nowadays. He'd mentioned emissions, but also the actually, quality acceptance of the vehicles. We can't actually have those tests and actually accept, approved vehicles flying up in the air until we understand exactly how they're going to be working, how fast they're going to be working, what they're going to be made out of, and all that stuff. And a big thing that's stalling that is actually a lot of hypersonics testing infrastructure. It's very difficult to test these vehicles up in the air because there's a lot of regulations on how quickly you can fly in the air currently. You also can't really test these on the ground as much because there's a lot of research facilities that simply do not have the capabilities to test engines like this. So there's a lot of issues with that kind of stuff too. But moving on to some of the materials. So as I'd mentioned, for example, a when you're getting up into, let's say, the Mach 5 to Mach 8 range, I'm going to call it skin in a sense, but the surface of your vehicle could be getting up towards the 2,000, 3,000 degree Fahrenheit range. Current convention vehicles or conventional vehicles that are trying to sustain those temperatures today are typically built out of a combination of titanium and ceramic type materials. So there's one thing that's kind of been thrown around. It's been used on a lot of technology currently and also in the past. It's a type of material, or I guess a classification of material known as ablative materials. They're very much like the skin that we have, on our bodies right now, where you notice, stuff kind of peels off in a sense, and it's meant to in order to have fresh skin beneath it. It's very much the same with some of these vehicles too, where you're sustaining such high temperatures. It's actually better to just have some of the material on your vehicle just burn off in order to release some fresh material underneath it. Of course, that does mean you're losing part of your vehicle in a sense. So it does have a timeline in a sense for how long you can fly it for. And because of that, they've actually been getting into a lot of new types of technology as far as especially some of the materials that are going to be sustaining high temperatures like that. I think one of the coolest technologies that I've been hearing about recently, it's kind of getting into technology known as biomimicry, where we kind of take inspiration from things in the environment and we try and influence that in our engineering. One of them is actually having, I think it's, they have liquid sodium that actually they have going through the different surfaces of your vehicle, and it actually sweats through little pores. And it's almost kind of like how, us as humans sweat, how plants and stuff, how they release water in order to cool themselves down. It's meant actually to relieve some of the heat that's being generated in your vehicle, as like, it's almost like your vehicle sweating in a sense. That's one of the really cool things that I've heard about. I think the Naval Research Laboratory here in the United States, I think they're doing some work on that. And I really hope that it's promising, because it'd be very cool to hear about, a hypersonic plane that's literally sweating in order to keep it
sort of like
cool.
the opposite of the de-icing technology that we use.
Exactly. Yeah. Yep.
That's so cool. Eric, can you discuss a little bit about what the Navy is doing with the next line of warships, what they're talking about?
Yeah, so I'm always monitoring different things for different reasons, and they released a model where this model of the next warship, as we discussed in our virtual green room, armed with hypersonics, but at the same time high-powered combat laser countermeasures for hypersonics, which gets into what we're discussing for navies. I know Commander Grimes obviously has experience in the Navy, but in particular the Eastern Med. And I kind of wanted to hear, you have the strategic discussion of the Med, but you also have the ramifications on materials, right? Because you're talking about a tighter area. So if I could hear your thoughts strategically, Commander Grimes, on, I know you have extensive experience in the Eastern Med, particularly Suda Bay, et cetera. What are you?
Yeah, and so the Eastern Med is a very it is a very important theater, and it will be, and it is the most important theater. And if you look, we talk a lot about this arc of instability that extends from Algeria into Tunisia to Libya. It works its way up to Egypt, up to Gaza, and then now, of course, Syria and Turkey. But actually, that really extends its way up through the Republic of Georgia into Crimea and Russia in the north. And of course, you talk about the ships. We currently run ballistic missile defense patrols in the Eastern Mediterranean. The base supports these operations, and these, with this new destroyer concept, one of the great challenges we're facing is that all of the countermeasures to these hypersonic weapons require immense power sources, whether it's a directed energy weapon or a laser weapon. You have to have this incredible source of power that is mobile, right? And you also need an incredible source of power for the early warning and detection systems too that are associated with it, right? Combined with the space systems that you have in orbit. And of course, the Eastern Mediterranean, with its potential to actually produce more oil and gas than all of Azerbaijan and Russia combined, is going to be the center of, of the, it'll be the theater that will have the greatest impact on Western civilization, as it always has.
What makes it also a great theater, Demetri, is that the fight can take place there, and people don't have to lose their populations. They just let the Balkans, the East Mediterranean people get killed.
Right, right.
I mean, it really is. It's great to see discussions like this beginning, because it really, people just are not aware right now of it's great that we're having all these technological advances and such, but it's changed the whole dynamic, right? So with these weapons, traditionally we could deploy, some Aegis cruisers and provide the necessary defense based on, mathematic formulas of trajectories. And you showed the map earlier of our North America's defense systems, right? But we're beyond, these weapon systems can be hidden in plain sight on a container ship, or and can bypass these, traditional weapon systems that we've invested so much into. We still need them, but what we're not preparing for, I think, as well as we should be, is investing the resources in intelligence and artificial intelligence and cyber security. All of these things are going to be required just to keep track, to serve as a deterrent to these technologies that.
Yeah, we have discussed countermeasures, and a couple of you, including Eric and Demetri, talked about laser weapons. Obviously, these hypersonic missiles or what have you are going at very high speeds, and there's very few things that could stop them, quite frankly. This is an open thing. Can anyone discuss some of the laser aspects, that countermeasure aspects, or any other type of aspects that are countering some of these hypersonic weapons?
Well, I just touched on, the Navy has been experimenting with directed energy weapons, but again, the limiting factor on that is that, condensing being able to provide the power that's required, to actually make.
How far can that travel? In other words, that type of energy we're talking about, how far can it travel? To stop something.
I'll leave that to one of our scientists, but
well, what do you guys think, man?
It's not that far.
No, I don't think it's that far. What do you guys think? Adam, Robert, anybody? Eric?
So can't necessarily speak on the lasers. Sorry to say that's not my cup of tea scientifically, but as alternative means to lasers for defense systems, we can sort of mirror what we've been doing in the past, which is designing and fielding interceptors that move at the same, or at least the same or potentially faster speeds than the incoming projectile. Right, what that means in the hypersonic scape is you just have hypersonic interceptors, right? Same sort of kinetic solution. There was actually right, think of the Iron Dome, right? That's exactly what the Iron Dome does when it receives threats from Hamas, right? With their Qassam rockets, right? So what's interesting there is that Raphael, who does a lot of the work in Israel on the Iron Dome defense systems, they actually, I think there was a contract at some point recently. It was either with Raytheon or L3Harris. I can't remember the exact name, but it was one of the defense primes in the U.S. to make like the United States' own Iron Dome for hypersonic interceptor capabilities. I couldn't say much on the state of that effort now, but that's an alternative solution to lasers. Right?
I remember years ago. We a lot of people were laughing at Reagan. And as a matter of fact, they used to call him Ray Gun. Ray Gun. In other words, that he was completely out of his mind thinking about some of the things that he was talking about. Eric, you want to discuss that in a second?
Well, for one, combat lasers do work. In this case, they have to be higher powered due to the nature of what they're taking out. But due to the nature of where we live, we're actually privy to a lot of information. So we're not far, 4 of us are not far from the Space Coast. The Space Development Agency announced a short time ago that what they were planning to do was launch a constellation of appliance satellites. If I recall correctly, use infrared signatures to monitor hypersonic lifts and also to track in real time. Now, the data is very sensitive. I have my own background. Some people know what it is.
Don't give us anything that's sensitive here.
No. But the data needs to be processed very quickly. So someone had commented on AI, but you also have limitations. You also have to take into account being spectrum denied. So apparently all these discussions are occurring if you follow the articles, but a lot of the tracking will be appliances. Then of course the last tier is your own system. If you're on the ship, obviously there's going to have to be, if you don't have data being sent to you by line of sight optics or however, you're going to have to be using rapid targeting. But these systems are just, they're upping the power. And again, the question is, it needs to, as Commander Grimes said, be moving around. My question for everyone to think about, again, on the Eastern Med, you have the Eastern Med, particularly in why I give a lot of credit to Greece, you have large continents on either end. So now we're talking hypersonics that could be used by whatever element launched from a continent. Just throwing that in there. Any thoughts on that?
Well, let me ask you guys a question, and Demetri, please, join in this. There's a lot of highly technical people in the East Med. We had mentioned Israel, for example, what's taking place in Israel. And I'm willing to bet that throughout the Middle East, including in Greece, that there's a lot of engineers, highly technical oriented people. And I imagine the US Defense Department is scrambling right now to try to pull in different people, different groups, different aspects of this particular thing, because we're way behind. What's your thought on the technical aspects and what exists in the East Med?
Well, so one of the great things, having Israel as an ally is they've actually taken a lot of the weapon systems that they've procured from us, and they've innovated those, right? So I was a naval attaché in Israel for several years in 2007 to 2009. So I got to see another country's war going on, Operation Cast Lead, dealing with the Katyusha rockets and everything coming from the Gaza. And, the Iron Dome at that time, the Iron Dome concept was still in its infancy. And it was basically Israeli engineers that understood what was called the close-in weapon system, the CWIS, which is actually the last line of defense. If you look at a US Navy warship and you see a device that looks almost like R2-D2 with a little barrel sticking out of it, that's what's called the CWIS, the close-in weapon system. And that basically just fires a wall of lead in the direction of an incoming missile. So it's a close-in because it's only effective. It's just putting up a barrier to destroy what's coming in to minimize the impact. And so the Israelis actually took that concept and expanded it into a longer range to provide what is called the Iron Dome. But again, that system requires some massive replenishment as well, right? So, every system obviously has its capabilities and limitations. So, if we can get into, a laser version or a directed energy weapon version of the Iron Dome, then, we're better off. But again, what we're seeing with these technologies is that we are really going to have to develop the closer in weapon systems even more and better because again, like as was explained, we're no longer dealing with a classic, math problem of an arc, right? And again, these weapons are going to be deployed in sleeper states in the form on container ships or at truck stops, and the implications are great. Whether it's the Eastern Mediterranean or here within our own hemisphere, where we have 6 failed nations, Cuba, Honduras, Nicaragua, Venezuela, Bolivia, and now Chile, which is, have all said that they're going to engage in closer military ties with the Chinese, So
Well, also the Russians in terms of Cuba, et cetera, where the Russians are making bold statement. Quite frankly.
Exactly.
Eric, you're dealing with some universities in Greece, Thessaloniki, Crete, et cetera. After listening to this discussion, what's your thought process in terms of those engineering schools and some of the research that they may be doing?
So I was fortunate my last trip, and I alluded to it, I didn't mention much. Just a couple of universities in Thessaloniki, and when I went to the NATO base, I was fortunate to actually speak to a couple of professors who may be watching now, particularly about the technology, and they're particularly accomplished in ICs and a couple of other areas that do apply to this, and it kind of gets into U.S. policy on technology transfer, development, distribution. I from what I know of things, and we're fortunate being in Central Florida. We're at the center of many things going on. But the DoD, and these are public statements, as if they were trying to figure out how to get to the partners and allies and bring them into the fold and all of these things. So from my perspective, there's talent in Greece to discuss at the university level with graduate students and to bring in the fold here. But it's not a zero. It's something where you have to onboard folks and take their talent and get them moving. It's kind of like we have two researchers here. They didn't just all of a sudden start researching hypersonics. They went through a certain path, and they have colleagues. We need to bring our allies, in my view, allies and partners, along with cyber, hypersonics, all these conversations, and not just conferences, but functional operations, which kind of gets into which was the first conversation I had with Adam, actually, was cyber and what that is. There's another, gets what Commander Grimes was talking about, velocity of transactions, the DoD, and I'll let Adam explain it. But there's defined reasons these cybers exist, cyber methodology exists, and it's actually getting around a problem that needs to be fixed. So if you could speak to that, Adam, and it kind of gets even what we're talking about with the Iron Dome in Israel and how they're operating. So if you could give a few words, please.
Sure, yeah, absolutely. So the SBA, Small Business Administration in the United States, they come out with, they came up, I think it was either in like maybe the 70s or 80s, but around that time, they came up with this idea called the SBIRs and the SITRs, and they're acronyms. So a SBIR, SBIR, is a Small Business Innovative Research proposal, and the STTR is a Small Technical Transfer Research. And the difference between them being the SBIR is more geared towards smaller businesses, and then the STTRs have like a component of academic research there. Right now, these programs have been very useful to the United States in accelerating R&D efforts for aerospace and the Department of Energy, and even NOAA, the National Oceanic Administration, and really is researching fundamental problems, coming up with solutions to these problems, and then developing commercialization and marketing strategies to actually transition these technologies to actual applications, right? The DOE even has SBIR and STTR programs. That's how useful these things are, right? And testament to their ubiquity, right? So SBIRs and STTRs are exactly how university labs such as ourselves at the Pearl, that's what we leverage in order to generate money, and also in order to accelerate the state of the art in these in the hypersonic propulsion technologies that we use. What we're seeing, if you start looking at the solicitations that the DoD is coming out with, a lot of them hypersonic. They're coming out with a lot more hypersonics solicitations and novel propulsion related research efforts in recent solicitations, which is good. It means we have a mechanism in place in the country to further accelerate the transitioning of these technologies to fieldable applications, right?
Robert, you the conversation you mentioned earlier was fascinating. Well, you were talking about something like a sweating mechanism to cool down, some of these missiles. Where is the research going in your mind? In other words, the research is taking place obviously right now, but what's really out there in terms of research that may be happening in the future?
Yeah, absolutely. So one of the things I actually, I guess I didn't get the chance to clarify during the initial portion was that what's important to know about these different hypersonic vehicles is that they're finely tuned to a specific type of flight that they need to do. So for example, even a very specific, speed that they're going, that heavily influences the design of the entire vehicle, from the geometry of it to the design of its engine to the type of materials that you need to use for that. Because of that, if you were to design a vehicle for, let's say, a Mach number of 4.5, it could be a completely different vehicle and a completely different design process than what you would have for something maybe flying at Mach 4.6, even a small difference like that. So I think being able to have an iterative and almost like a standardized process for being able to, design and manufacture these hypersonic vehicles without having to spend, 5-10 years trying to, figure out just one vehicle. If we can have almost like a streamlined process or approach to being able to design these, that would naturally, expedite all the further research and all the further development that we have. So I think if we can spend some time going into, maybe being able to parameterize some of the designs, being able to, understand a bit more how these work and how we can share components and such between different types of vehicles, I think that would save us a lot of time up front. And also, we kind of got into this a little bit with the SIBRs and such too. It would be very helpful also for just in general, the community, at least specifically in the United States, if we can also have a bit more collaboration in a sense. There's a lot of really great research that's being done, but a lot of it can also sometimes be kind of, hidden for a little bit. And it's very difficult to find all of the useful knowledge that's being, developed either at these research laboratories or these universities. We need to be able to have a better way of collaborating and making sure that everyone understands what is actually being done as far as hypersonics work is involved.
This has been an absolutely fascinating discussion, quite frankly, that we're going to continue in another series again. But what I'd like to do is start wrapping up this particular panel discussion. And I'd like to start with Eric, some final thoughts on this particular topic or anything you want to discuss around it.
Well, for me, we're at the crossroads of technology, culture, and obviously business. And what we were just talking about, how business and transactioning is a national security issue because you can't fund research. On the other hand, you're talking about people, you're obviously always talking culture. So it was important for me when we met and discussed this to bring up this topic in a format that's a friendly discussion that can expose the broader community or communities that we belong to. So I personally would like to thank Adam, Robert, Commander Grimes coming in at the last moment. Thank you very much and adding your perspective, all of you.
Adam, some thoughts on the topic?
Yeah, absolutely. So first of all, it's with great pleasure and sense of duty that we're here today to talk about these issues as some of the next generation engineers and leaders who are going to be at the forefront of this landscape, right? So I think two things I want to sort of talk, one, just briefly a little bit about propulsion, right? So most propulsion systems are very complex for hypersonics, and propulsion systems are the very foundation of the design of hypersonic vehicles. A lot of conventional subsonic vehicles, they're a little bit more plug and play compared to hypersonic vehicles. So Really, the biggest difference is that, at the forefront of, at the very start of design for a hypersonic vehicle, you need to know what your propulsion system is. And these propulsion systems so far are looking to be very complex and heavy and have a lot of moving parts. So what we're doing at UCF is we're working right at the forefront of SCRAMJETs, shock-based, detonation-based propulsion, hypersonic propulsion concepts that can reduce costs in fabrication, reduce part count, and overall system complexity. That's where we see the, just to sort of piggyback where Rob was talking about the future of the hypersonic state. That's where that's another area where we see the future of hypersonic propulsion evolving. So the second thing, right? So we talked a lot about the technical and some of the non-technical issues involved. Where do I fit, or where do I see things going? I'm sternly optimistic that the technical challenges can be solved rapidly in time, given that the United States is becoming more aware, not just in the government, but the citizenry is becoming more attuned to these developments. But on top of that, what could help the development even more is to really just accelerate this awareness and these talks that we're having for hypersonic developments. But otherwise, yeah, in short, sternly optimistic that we'll meet the demands of American hypersonics. So.
Robert, some thoughts on the topic?
Yeah, absolutely. Adam really touched on it on the end, and also with regards to the research that we're doing here at UCF as well. But hypersonics technology it's very advanced. It's very incredible to see what we can kind of achieve as humanity. But a big part of that is it's a big responsibility for all of us. And as Adam had touched on this, it's really important to have these kinds of platforms that we can talk about this and share all this knowledge to everyone, because there's no way for us to be responsible about the use and the development and having this technology unless everyone understands what the implications of this technology are and really what it can do here in the world. We're all here on the same planet, and we all got to understand what we can do with the technology that we have. So it's important that we all be responsible with it. So I also, again, I wanted to use this moment too to also thank you again, Lou, and thank you everyone for being able to have a conversation honestly like this.
Robert, thank you so much, and Adam, of course, and everybody on the panel. I want to do this again in the next few months, by the way. We'll go into it again, in maybe even more depth than we've done today. Demetri, thank you for jumping on board and helping us in this particular panel discussion. Some thoughts on what we've been talking about in terms of hypersonics.
Yeah, I appreciate you having me on, and it was a really great discussion that spanned a lot of the issues from the technical to the non-technical, and it seems like I can't find every time I meet people who I learn new things about this this technology, which is going to be at the forefront of all of our lives here very soon, actually. So thank you, Lou and Eric, for putting together this group, and I look forward to joining in future discussions.
No, absolutely. We're going to have another panel discussion with regards to hypersonics. Absolutely, with you guys. It was fantastic. Demetri, I wish you all the luck in your candidacy, congressional candidacy in Florida. We're here to help. As a matter of fact, all you guys are basically, except myself and Costa, who's in Athens, you're all in Florida, actually. So it's absolutely amazing. To the audience, as you can see, this was an amazing discussion with a great panel. I'd like you to join us in a couple of weeks. We're going to go in a different tangent and discuss the revolution of 1821, in particular, the Hellenic cotton merchants who had a tremendous effect on the Civil War, something that's never been discussed actually in any panel, quite frankly, and something I think that after we have the panel, there'll be tremendous research in this area and how, in fact, those Hellenic cotton merchants who came in to the United States before the Civil War and were here during the Civil War and after the Civil War, how they actually affected the outcome of the Civil War. To the audience, so join us on February 6th for that particular event. Our events are obviously on our website at www.embca.com. And I'd like you guys to subscribe to our YouTube channel, which is under EMBCA, EMBCA. There's no charge. And we always have fascinating discussions and fascinating guests and panelists. Again, to the panelists, you guys were tremendous, an amazing panel, a very important topic to be discussed again and again and again, so the public can understand what's taking place around the world and of tremendous importance to this particular nation. Thank you all. Thank you, panelists, and thank you to the audience who was with us today. Thank you, guys.
Thank you all.
Thank you.
Thank you.
Thank you.